Okay, so it's recording. So I'm just trying to figure out the best way to do this. Maybe just looking at this, sharing the slides, probably the best approach. Hold on, let me do that. So here's the slide. We've got everything nicely drawn. Share screen. Okay, so I'm sharing the screen and here we are, reasonably big. So you've got and or invert, and this one is 2211. So basically there are four numbers, 2211. So each of those four numbers refers to an input to the final OR gate. And then the 2, the 1, 1 says the first input is 2 inputs to an AND gate. Then another 2 says there's another 2 inputs to a second AND gate. If you've got ones here, then doesn't make sense to have an AND gate with one input because, of course, it's just the input to the output's the same. So you skip the and go straight into the OR. So it looks like this. So you've got 2 inputs on one AND gate, 2 inputs on another AND gate, 2 single inputs, and then all those put together on a final OR gate. Then the OI is the other way around, but the same principle of numbering. So 221, then got 2 going into one OR gate, 2 going into the next OR gate, 1 just going straight through. All those go to an AND followed by an invert. Does that make sense? Just asking that question before I move on to the next question. Do you want me to do another example, or is that good enough? Okay, so then T sizing, why do you calculate the parallel of the series combination? Oh, so you're talking here about in T sizing when we are working out the widths. Yeah, let me find you an example. Because that generally is easiest to go with examples rather than anything else. Is that the right sort of? I think this example here actually does what you're interested in. Okay, I think this is, tell me if I'm wrong, but I think this is what you're asking about. So you've got, okay, this example is doing the deepest stack first. I think it's the shallowest stack first that actually you need to look at, but let's just look at the deepest stack first. So we've got 3 here on the end side. So we size them at 3 WNI. Yeah. So that makes sense. But then when you come here, this one's already 3. And the question is, how do we size that? Is that basically where your question is in terms of parallels and series? Is that the right sort of question? Yeah, okay. So maybe best if I scribble this down. I don't know, can you see my visualizer? Am I drawing at the same time as I share the screen, or do I need to stop screen sharing? Let me know. I'll just draw on the basis you can manipulate Zoom at your end, but if you can't, let me know. Good. Okay, so that was basically the situation. And what we did was we went down this way and we said the stack depth was 3. So because the stack depth was 3, the sizing is 3 WNI. And then we start thinking about this direction here, which is slightly more problematical. So what do we do about C? Well, we know that D has width 3 WNI. And what we're wanting to do is to find the width of C. And remember, what we're trying to do is we're wanting that basically the equivalent resistance, if you like to think of it, or impedance from Z through to VSS is always going to be the same. So just going back to the left-hand side here, we say the stack depth is 3. Therefore, if you size them at 3 WNI, that gives you back the same effective impedance, because you've got so I tend to think about the transistors in this context as the wider they are, the lower the impedance, and the impedance of the transistor is proportional to 1 over the width. So if you make the width wider, it's got a lower impedance. And so if you've got 1 over 3 WNI, that's its impedance. Then you've got 3 of them in series. So so add resistors in series. Sorry. And you end up with 1 over WNI. And that, of course, is the impedance of a single transistor. So that's equivalent to your inverter. So that's equivalent to inverter. Okay, that's the same as your standard inverter, 1 over WNI. So then you do exactly the same thing coming down this side. But we know that D is sized already to 3 WNI. So on the right-hand side, which you can't see, hold on, let me adjust things so you can see what I'm doing. So on the right-hand side, width of D is 3WNI. So the total impedance is going to be 1 over 3 WNI plus 1 over the width of C, which we don't know. So I'm just going to call it width of C. But that needs to all add up to the unit inverter. And then when you rearrange all that, of course, you end up with the value of 2. So you take this across, you would so I need to run out of paper, that's the problem. Let me expand that. Right, set up. So what we had was 1 over 3 WNI plus 1 over WC equals 1 over WNI. And if you wanted to do everything explicitly, you would say 1 over WC equals 1 over WNI minus 1 over 3 WNI equals 2 over 3 WNI. That's 3 over 3, that's 2 over 3, and WC equals 1.5 WNI, which is what it was on the slide. And basically, yeah, it's the same equation as dealing with resistors in parallel, is the way I think about it. Does that make sense as a way of working it out? So what we're doing is we're going down the stack and wanting it to be equivalent to a unit inverter, and remembering that the impedances are 1 over the width. So that's how you calculate it out. You're wondering why you do it in parallel. Well, the reason is that if you've got a transistor, where do I start the explanation? If you go back to what we're trying to do, we're trying to get in T-sizing, what we're trying to do is to get the timing to be equivalent to the unit inverter. And if you remember with the unit inverter, if you work out the delay times for the unit inverter, they're based on essentially RC. But when you calculate it all out, the effective impedance of a transistor is 1 over the width. Okay, so for a transistor, if you just draw a transistor, source drain, that's the width. If you've got a bigger width, you've got a smaller impedance. And then it will drive the next gate more quickly. Okay, so what we're doing with the stack is we're looking at the total impedance of that stack, and we're saying we want that to be equivalent to the impedance of a unit inverter. And so we are adding 1 over W's because the impedance goes as 1 over W. So impedance varies as 1 over the width. So if you double the width, it's half the impedance. And that's why we need to do it that way. Okay, is that good enough for that one? Any further questions? I think I've answered them both. Elmore delay. So question 1A 2021. Let me try and find that question. Hold on. 2021. Let's close that and copy, take the examiner question over. So is that the right question? That's question 1A 2021. So we've got an output from the inverter. We're going to X. So we're given the width of the tracks. We know the resistivity. We know the parasitic capacitance. As a capacitance per micron. And we are asked to calculate the delay. Right, so if you remember with Elmore delay, that what we need to do is to, first of all, calculate all the intermediate resistances and capacitances. So I'm just making sure I follow the same route as I followed before, so I'm not doing it totally differently. So I'm just looking up what we've done. So I'm not making it up as I go along. So first thing you want to do is you want to draw out from the output of the inverter, which is B, through to X with all the different nodes and changes. So that's B, that's X, and you've got a node at C, and you've got a node at D, and we've got some distances here, which are 100 microns to C, 150 C to D, 150. So what we're going to do to start with is we're going to ignore the side branches. Remember that if you ignore the side branches, you get a slightly optimistic picture. That's fine. That's what we'll do to begin with. We need to work out the different resistances for each of the sections. So if you look at B to C, the first thing to do is to work out the resistance and the capacitance from B to C. And the resistance, you start off with that. It says the tracks are 0.25 microns wide and 100 microns long. So resistance is going to be 100 microns long divided by the width multiplied by the ohms per square. So that's the number of squares and that's the resistance per square. Okay, so basically the way ohms per square works is that if you've got a single square of the material and you're going from the left side to the right side of the square, that's the resistance. But if you've got two squares, one after the other, then you double the resistance. And if you've got 100 microns long, quarter of a micron wide, that's 400 squares, one after the other. So 100 divided by 0.25. So if you calculate all that out, that's 400 times 0.15 equals 60 ohms. Okay. And then what we need also is the capacitance for that section. And if we want to do the capacitance for that section, we need to look at the parasitic capacitance, which is 0.2 femtofarads a micron. So it's 100 microns long, multiply it by 0.2, so it's the length times the parasitic capacitance per micron, and that'll give you 20 femtofarads. Now, I'm aware that's a slightly different calculation to some of the other examples. Sometimes you're given the area capacitance as well. And you've got the area capacitance, which is net capacitance between two different layers. Then you have to work out the area and multiply it by the area capacitance. In this situation, you weren't given that. You were just given the capacitance by length, which makes your calculation easier for you. So you don't have to guess a number, you just say, you assume it's 0. Well, actually, you'd assume it's rolled into the per unit length number. So we've now got a capacitance and resistance for the first section. Again, in this example, sometimes in examples you're given tracks on different metal layers and told that when you move from one layer to the next layer, you're going through a via which has a certain resistance, and you have to remember to add those resistances on. In this particular example, you're not given that information. Possibly it's all in the same layer. It's not a problem. So you don't need to consider that. So what you do need to consider is the capacitance and resistance of each of the sections. So we've done that for the first section. And once you've done it for the first section, actually the second and third sections are going to be pretty much identical calculation, just with slightly different lengths and therefore slightly different numbers. So if you look at C to D, the only difference C to D is that your length is 150, so everything's multiplied by 1.5. So the resistance equals 150 over 0.25 times 0.15. And it's just 1.5 times what we had before, so it's going to be 90. Whereas the capacitance, well, that again is 1.5 times what we had before. So that's going to be 30. Sorry, somebody's got a comment. Ours, I think 90 for 1.5. Yeah, you've corrected it there. And again, D to X, well, the resistance is the same length. The resistance is going to be the same. But the capacitance now, we've also got to bear in mind, we've got the capacitance at X at the end. So the capacitance here is going to be 30 femtofarad, that's for the wire, plus 30, and that's from X, equals 60 femtofarads. Okay, so you need to take into account the final capacitance. So generally speaking, Elmore, this is one of the most important and difficult stages of the calculation, working out all your resistances and capacitances. So that's the first stage. Once you've done that, what we need to do is to put it into the equation, and then the answer should just come out. So the equation basically, if you remember, is a load of RCs, but at each node, so to charge up each capacitor, we've got a bigger resistor. So we think about it as a lumped circuit, which goes something like that. I need to put in my grounds. And we've got R1, C1, R2, C2, R3, C3, for instance. And then the delay is just R1, C1 plus running out of space. So it's basically that which you write as a double summation. So just put in my capacitance. So you're summing the resistors from J equals 1 through to I for each capacitor I, and then you're going from I equals 1 to 3. Of course, in general, you'd have more than 3 stages. We just happen to have 3 in this case. And I think typically in an exam question, 3 is a sort of number you're going to come up to. You're never going to have 1. 2 is a bit small. 4 is getting a bit big. So you might get asked 4, but it's getting towards being a bit nasty. So generally speaking, you'll probably find most exam questions end up with 3, just because it's a sort of big enough number to show that you know what you're doing, but not so big that it makes for a huge amount of arithmetic work. So generally, that's the sort of number you'll have to deal with. So that's what we need to do. We've worked out all the numbers for the capacitors. So all we need to do is put the numbers into the equation and add them up. So if we do that, we get oops, I brought up the solutions here. I'm just putting up the solutions for myself to make sure I get the same answer as I got last time. Because I'm very good at making arithmetic mistakes, as we all are, especially when I'm talking to people at the same time. So R1, we can just remind ourselves, we've got three R's we worked out. We call them R1, R2, R3, were 60, 90, and 90. Our capacitances were 20, 30, and 60. So those are the numbers. And what we want to do is to just plug them into this equation. So we get delay equals R1 C1, which is 20 times 60, plus you sum the resistances. So it's going to be 60 plus 90 times 30 plus 60 plus 90 plus 90 times 60. And yeah, rather than doing that, I'm going to take my answer I got from last year and call it 20.1 picoseconds. But I'm sure you can work that out yourselves. It's 120. There's 100, it's 1,200 there, and so on. So you can go through and work all those ones out. And obviously, when you get to 1,000 femtos, you get to a pico. So that's 1.2 picos comes from there. That's 150 times 30, which is 4.5 picos, and that would be bigger again. So that's basically it. So that's the answer. It doesn't ask you for the. Now we did in the lecture, we did pessimistic one. I mean, sorry, not. We said this is slightly optimistic, and there's a way you can do it slightly pessimistically by including the capacitance in the node E to C and F to D and adding those in. And that will give you a pessimistic answer. If you look at this one, it's only worth 6 marks. So this is sort of exam technique. And you'd say, well, you probably doesn't want me to do the calculation twice for 6 marks. So just leave it like that. And that's the basic answer. Okay. So somebody's asked me, can I explain the second and third questions in 21 years? I presume you mean for the exam in 2021, rather than taking 21 years over it. So looking at questions 2 and question 3, I think is basically what you're asking. I can go through them briefly. I'm not going to have time in 10 minutes to give you a complete description of the answers here, so I can just give you a quick talk through. So the first question A, it wants the logical expression and what family of logic does it belong to. Right, you should hopefully be able to work this out. If you look at the inputs here, you got in the N side, you got 4 in series and you got 4 in parallel on the P side. So it's a standard CMOS family of logic. 4 in series, that's a 4 input NAND gate. And you want to label all this. So to label this, you'd put your input A, B, C, D here, and the output Z there. Could I put the answers on the Moodle? No, we have a basic policy that we don't just put all the answers up there. So there are some answers to some past questions in for the tutorial work. And that's all the answers I'm going to put up there on the Moodle site. This has been school policy for a long, long time. But what I can do is if you make an attempt at these questions and get stuck, or even if you don't get stuck and get to the final answer, if you send them to me by email, I'll say, yeah, that's right, or I'll try and point out where you've gone wrong. So just on the basis of going through this really quickly, what's the T size? Well, T size in this isn't too difficult because we are putting those in series, so stack depth is 4, so that becomes a relatively easy bit of T sizing. And then what's a pre-charged logic circuit, which does the same function. And reasons for your design choices. Remember, with pre-charged logic circuit, you can either miss out the P side or you can miss out the N side. So if you missed out the P side, you would have a single gate transistor up on the P side. So it misses off lots of the P transistors. Whereas if you did it for P-type pre-charged logic, you would have a single gate type clock, I should call it clock, transistor on the N side. And so it's asked you to sketch one, and you can either sketch the P1 or the N1 and give a reason for it. Now, of course, if you do the N1, you're going to have a lot of transistors in series, which makes for quite wide transistors. Whereas if you do it on the P side, because they're in parallel, the transistors aren't quite so wide. So you might want to do a quick think about that and say, well, actually, if you did it at the P-type, it looks instinctively like, although P transistors are wider, because there's so many in series on the N side doing it the N way, you're probably going to save space by doing it P-type. So you want to think about that for a moment and then give reasons for choosing the P-type, because it takes up less space. And then draw your stick diagram. Now, I haven't got time to do a stick diagram in 5 minutes, but that's basically the same way as before. But this is a pre-charged logic circuit, so you don't have 4 transistors both on the P side and on the N side. You'll have 4 on one side and a clock one. Yeah, and again, colored pens and pencils can be used, but not essential. Yeah, definitely better to use color if you can. Oh, yes, last year, because it was online, we didn't give you a choice of 2 out of 3. We said you've got all your notes available, you're in your house, so we're going to assume that you don't get a choice. You just answer the 2 questions we give you. This year, that's no longer the case. As you know, you have a choice of 2 out of 3. Okay, so I've very quickly sketched through the solutions to that. I suppose I've done it so quickly, I've got 5 minutes spare. Is there any particular bit you want me to expand on? Maybe I could expand on C and D here, actually. We didn't talk about those. So why is the rising and falling delays at X not in general equal? So if you look at X, you'll have a delay when it rises and a delay when it falls. And the question is, why are they not equal? And what tools can you do to do something about this? Well, what you need to do for that, of course, is to think about what causes the delays. So the delays come from RC, effectively, or you're charging up the capacitor at X, and the speed with which the capacitor at X is charged depends on the gain of the transistors in the inverter, which is beta. Now, the thing to bear in mind is that when you've got a falling signal, then it's the NMOS which is pulling it down. And when you've got a rising signal, it's the PMOS which is pulling it up. And therefore, the gain of the NMOS transistor gives you the fall time, and the gain of the PMOS gives you the rise time. And so then the question comes down to, because the gains are not generally equal, but you can adjust them by adjusting the widths and all that sort of material which goes in there. And then crosstalk and capacitive coupling, and he wants the relationship between them. Again, so because this was an online exam, it wasn't something which you can just take straight from your notes. You have to think about it, and you have to think, well, what's crosstalk? What's capacitive coupling? How are they related to each other? Well, capacitive coupling is when you've got a capacitance between 2 tracks, and that gives you some effects. And likewise, crosstalk is one specific effect of that. So capacitive coupling is broader. So in other words, crosstalk is one particular implication of capacitance, capacitive coupling, but capacitive coupling also gives you delays, for instance, in the final output. So this question, D, you have to sort of think about what the 2 things are and how they're related. So yeah, so someone has asked, is it easier than online? So the online questions were probably slightly harder from the point of view that there was more thinking involved, but you should find there is some thinking involved in a normal exam. It's just that because you can't look things up, we have to allow for that fact. And so you probably find the online ones slightly harder. Yeah. Okay, so it's pretty much time up.